Um, Welcome everyone, thanks for joining today. So in this talk, I would basically be describing how we know about the universe and how do we actually study it, and most importantly, connecting it to the kind of research that we are doing at RRI to understand our universe. Before we really get into the actual history of the universe and what we are trying to do, the first thing to know about is how vivid the universe is when we look at different parts of the electromagnetic spectrum. So typically when we look at through our own eyes, we see something like this. So this is Milky Way Galaxy, and something that we are more familiar with is something like this. And let me see if I can make it more interactive. So when we look at the sky in a very remote area, we will see some parts of a structure like this. And this is nothing but our own Milky Way Galaxy. And we are basically looking at it as from the edge of the galaxy. And you see lots of lights, different colors, and because our eyes are tuned to detect these. But this is not the complete story, right? We have different wavelengths that our eyes are not sensitive to. And when we build telescopes that can actually look at those wavelengths, we get a completely different picture of what our universe is like. So what I can do, I can scroll it through different kinds of wavelengths. So there are instruments that have been designed to look at the galaxy in very different wavelengths. And you can see that as we move across this whole spectrum of different lights, how the structures continuously change. So basically when we are looking at it through our own eyes, we see a very small part of what it is actually. And therefore we are moving from very high energy light, which is our gamma ray, you see something, and then X-rays, visible light of course, and finally we move up to very low energy light or very low energy photons, which is finally the radio, right? So basically we have to combine all of these different observations together to understand our own universe and how it has evolved. So let's go back to the slides. We have different instruments, right? So if we want to study our universe at a very specific wavelength or at a specific light, we have to design them very differently. Some of them we can design on Earth, deploy on Earth and study. So we are all familiar with optical telescopes. This is right here, very close to Bangalore. But there are some wavelengths which we cannot study from Earth, right? So for example, X-rays, because atmosphere does not allow us to do that. So we have to build satellites and launch into space to study those. And again, AstroSat being one of the satellites from India. So for studying different wavelengths, you need to design different telescopes. The one that I would be focusing today is the radio telescope. And the great part about this is our atmosphere is mostly transparent to the radio. So we can build a telescope on Earth, and this is right here in Pune, in India, one of the greatest radio telescopes that have done amazing science. And we can build similar telescopes around the world, deploy them, and try to study the radio waves that are coming from us, from the universe. So this is what I'd be focusing today. And how we do that? So basically, if you look at the universe as a whole, this is of the Illustris simulation, one of the most giant simulations that has tried to study how these different galaxies that we look around have evolved over time, right? So we know the current age of universe is around 14 billion years. And this is basically a simulation of how these different structures, these blips of light that you are seeing, actually grows with time. And this is what we are interested. That is, we know that it had some very early phases where there were no stars, no galaxies. And suddenly today, when we look at the skies, we see so many structures around us. So how did we transition from something that was so bleak to something that's so vivid and colorful? That is the evolution that we are interested in studying. And specifically at RRI, what we are most interested in is exactly this transition. So at some point we know when the universe was formed, there were absolutely no source of radiation. So it was just hydrogen gas, which is the most abundant element in the universe. But really there were no stars or galaxies back then. And we are talking about around 100 million years. And just for perspective, we are at 14 billion years. So really universe was just 1/6 of its current age. But at some point, we had these very first stars and galaxies that formed, something that we call as cosmic dawn. And this is a very crucial phase because that basically led us to the universe that we see today. So how this really happened, how these very first stars actually formed in an environment that was completely different from which we have today. So we know that there is a lot of hydrogen gas around, and there is a very specific radiation which is emitted by these hydrogen atoms. And we'll call it 21 centimeter signal without going into the depth of what it is. But what we want to do is to detect this very faint signature from the very early universe, right? And that is one of the wonders of astronomy, that is, the deeper we go, that is, the more distant objects we look at, we start to study the history of the universe, because light takes a finite time to travel to us. And therefore, when it comes from 400 million years back, it is actually telling us what that star was 400 million years back. So that is the kind of things that we want to do at RRI. Basically detecting these faint signatures that are arising from hydrogen atoms. And for that, we have to build these radio telescopes, and we have to basically observe the skies using that. But then the story is not that simple, and that's why this is a very active field of research. So suppose I want to detect this very faint emission coming from hydrogen atom, right? And this is the time when the very first stars formed, so this is coming from a very early part of the universe. But when we actually design a telescope, that's not the only thing that we actually receive in our data. We have our own galaxy, and we saw this before how bright it is. And compared to the signal that we are looking from the very early universe, it can be 1,000,000 times stronger. So in the units that we have mentioned, these are just brightness units. The signal that we are looking for, it is around 0.1, 0.2. And in the same units, our own galaxy is 10,000, 50,000. So what we have to really do is dig deep into this data that we get to find out something about the very ancient signature that we are looking for. And to make things worse, because we are on Earth and the kind of frequencies we are looking at, we also have terrestrial emission. So the last plot here basically shows how bright Earth itself is, because we have these mobile phones, we have FM, TV stations, and they all transmit signals at exactly these frequencies where we're looking for these very primordial signals. And these are even brighter than our own galaxy, right? So basically, when we observe through a radio telescope, we get a sum total of all of these. And then the question is, how do you separate out these very strong things to get back to these faint signatures that we are looking for? So it is like finding a needle in a haystack. But nevertheless, we have tried that. And the very first thing that you do is to cut down the last part, which is the interference that comes to us through the radio, television, through FM. And in order to do that, you basically go to as remote a location as possible. So if you look at experiments, these radio telescopes, where they are getting deployed around the world, which is what is plotted here, you will see one similarity, which is they are all deployed in extremely remote locations. So you can start from here. There is a telescope that is being deployed in the Arctic stations, to something in the Atacama Desert. Right now, we have deployed one telescope here in Ladakh. Then you have something at Marian Island, which is one of the remotest areas in the world, midway between South Africa and Antarctica. And then we have these deserts where people have deployed these telescopes. So all of these are very remote places, and the idea to do that is basically to cut down as much of an interference as possible. So now I'll focus on our part, which is the kind of telescopes we have been deploying in India. And the first exercise that I started off when I started my research is to look for which sites are possible. And in order to do that, we had a very portable telescope, which is what I'm showing here. This is slightly non-usual telescope. So when we think about radio telescopes, we think of these dishes looking at the sky. But really, depending on what we want to do, what we want to study, we can have different kinds of telescope. And this is one of them. So we took this, we just traveled around the country, and we looked at how quiet it is. Of course, in radio wavelengths, how far it is from the civilization, how less FM there is, and things like those. And these are some different places, from Ooty to Andhra to Himalayas, all kinds of places, to localize which sites we actually want to observe. And finally, we ended up choosing a few sites which are shown here. And again, as you can see, no signatures of human, which is great for us. So we can have very clean data that it does not have these interference that typically we see when we, for example, do the same in Bangalore. Once we have that, the next is designing the telescopes themselves, and which is a very tricky affair, because telescope can itself contaminate the data. No instrument is an ideal instrument. So we have to be very accurate in the way we design our telescopes. And as I said before, if you look at these telescopes, they are very unusual telescopes, right? Like spheres, they almost look like spaceships, but they are these radio telescopes that are looking at the very early part of the universe. So we have deployed them on land, we have deployed them on water for all different reasons, but the idea is to observe the skies and get to know about our universe. And of course, no observation can happen smoothly. So when we actually deploy these instruments, we see all kinds of things. We can see rains coming in and just drenching all our instruments. We have wildlife problems sometimes, yaks coming in Himalayas. Sometimes instruments goes bad because these are very remote locations, and then it's a challenge to fix it on the spot. Temperatures can be another problem. So we are talking about sub-zero temperatures, and therefore it takes a lot of courage to actually go out and fix some things. With the same temperatures, sometimes the transportation doesn't work. The only problem is it is in middle of nowhere, so we have to fix it ourselves. But in midst of all these hiccups, we finally are able to conduct these observations and get the first light, right? So we are able to observe the universe with our telescopes deployed in extremely remote locations. And that itself is a great feeling. And so we have skies like this where we have observed, this is one of the locations in Ladakh where we had observed. These tiny tents are where we had actually stayed. And we see amazing skies, very less interference from radio, but also light-wise, because these are away from any human civilization. So you get to see the entire what the galaxy is and what structures exist in the skies. And I'll just jump on to the last part of my talk, which is once we have the data from pristine locations like this, another challenge is how do you remove all these contaminations? So okay, we have removed human interference by going to remotest of the sites, but then we still have our own galaxy. We live in a galaxy, so we can't escape it. So we have these observations. Then there is another round of research in how to distill that data, remove all of this haystack to finally get down to the needles, which is what I'm showing here. So that is the kind of exercise that we do. And the final slide that I'll show is finally escaping Earth altogether, which is something we are doing at RRI, which is we have gone to the remotest of locations, but that's not good enough. So one of the quietest sites in the solar system actually is Moon, because when we have a telescope which is on the far side of the Moon, it is shielded from both the Sun and the Earth. And both of them are primary sources of contaminations in our data. So we have proposed an experiment called Pratyush. It is funded by ISRO. So we are developing this radio telescopes that will fly in space in lunar orbit, and it will conduct these radio observations of the universe from the far side. So with that, I'll close and take questions. Thanks.
Let's have just one or two quick questions.
So this Pratyush, which is mentioned here, this will be in the orbit of the Moon, or it will be on the surface of the Moon?
It will be orbiting the Moon. So the idea is that when it's on the far side, when it's not facing the Earth, it will actually look into the sky and do these observations of very early universe. And then when it comes, because it also needs to transmit the data, so when it comes on the other side, when it faces the Earth, it will do the rest of the things.
Sir, if there's any disturbance after the launching of any satellite, what will be the process of it?
Right. That's one of the disadvantages of space missions. When you have launched, there is very little that you can actually do. Of course, people can take corrective measures, but it's difficult. Therefore, for any space missions, it is essential to demonstrate its working in the lab. We have to go through a series of tests to make sure that it will actually work in the space before we actually fly it.
Sir, while you are collecting some data from your supercomputer MacBooks and all, like what type of backup do you have if you lose data?
Great question. It's a very non-trivial question because the data loss is really one of the most nightmares of all researchers. So we basically have, for example, when we go to sites like these, we don't have internet. So we basically have multiple rounds of backups. So we have data on our computer, but we also carry these external hard disks. We have a primary backup, and just to be double sure, we also have a secondary backup. So just in case if one thing goes bad, we have other options. And the moment we come back to the civilization, we upload all of that on cloud, so it is safe for a longer time.